I'm just going to have introduced Dr. Lagos so that he can introduce our speakers. Dr. Lagos is a busy man. He's Associate Professor of FIU's Moss Department of Construction Management, Director of Research at FIU Applied Research Center, and the Director of FIU's Science and Technology Workforce Development Initiative, also known as DOE Fellow Program. Dr. Lagos is also a PI and co-PI on several sponsored research projects. Dr. Lagos has over 28 years of hands-on experience in executing, managing, and leading research programs sponsored by the federal agencies and private industries. Since 2012, Dr. Lagos has been the principal investigator for the DOE-FIU Cooperative Agreement, conducting multidisciplinary research in areas of robotics and remote systems, AI, LM, generative AI, cybersecurity, natural language processing, radiochemistry, environmental chemistry, decommissioning, and digital decommissioning. Dr. Lagos, you have the floor. You can go ahead and introduce our speakers. Thank you.
Thank you, Walter. I hope you can hear me well.
Yep.
Great. So it's a pleasure to introduce our speaker for today's Tech Talk. We have the pleasure of hosting Bryan Steinfeld from Los Alamos National Lab. Bryan, thank you for participating. We're looking forward to your presentation of the robotics project that you guys are doing at Los Alamos. Bryan is the Deputy Group Leader for the Automation, Robotics, and Control Group, also known as E3 at Los Alamos National Lab. He has worked as a robotics and controls engineer at Los Alamos since graduating from UT Austin with a master's degree in mechanical engineering. That was in 2009. And he also has a bachelor degree from Rice University as well. He has worked on a number of controls and automation systems throughout the lab in DOE complex, throughout the DOE complex on a number of applications, right? Robotics application for D&D and decommissioning. Since 2020, he has also served as the Los Alamos representative to the DOE Interagency Group, led by the Office of Technology Development at DOE, Rod Rimondo's office, and also with Anna Marie Daniels. And I have been personally seeing some of the presentations that he had made and contributions he had made to that group, to that interagency group. So with further ado, I introduce and present to you guys Bryan. He's going to do an amazing presentation. We're looking forward to seeing Bryan's colleagues here next week for our robotics and AI workshop that we're conducting next week. I know that his colleagues are going to be presenting some of the research work and challenges that Los Alamos has in terms of environmental remediation and how do we apply robotics and AI to those type of problems. So I'll turn it over to you, Bryan. Thank you for joining us, and it's a pleasure.
Great. Thank you so much, Leo. And yeah, like you mentioned, I'm sorry I won't be able to make it there next week, but very excited. Dr. Boardman and a few others will be able to attend, and they should have some good updates and good talks to you as part of the workshop there. So it's very exciting, and sorry to be missing it here, but happy to be speaking today here too. So this project in particular really is targeted at one of the kind of things really that we're dealing with in the EM side, so the environmental management side in the first place, which is site characterization here too. So I'll talk about this too, but what we're talking about is really the kind of development of these robotic systems to perform the tasks that are traditionally performed by engineers, technicians that involve really putting themselves in areas where contamination is present and putting themselves at that risk of exposure there, and to additionally just kind of incur that kind of lifetime exposure here too. So what we're dealing with is a ground robotic platform, and this is specifically targeted for radiological contamination here too. So as Dr. Lagos mentioned, so this is a project that was sponsored by the Technology Development Office. I know Leo's has a long kind of standing development partnership with them, and we really appreciate all the kind of partnerships we've worked with on him too, in addition to some of the work that involves with some of the wearable systems here too. But for this system, we really had two goals on this here. So first, the kind of end goal is we wanted to really deliver MARSIM data, and I'll go into what MARSIM is too. But what this is basically, as we're talking about characterizing a site that has been previously contaminated or used for various degrees of radiological work, there's contamination present, and you're trying to quantify how much of that is and how confident you are about the kind of various levels too. So really that targets on two ends, kind of, how contaminated is the site before you go in and perform any remediation activities, and how, contaminated is after you're completing them, to verify that that work is done and is free to release here too. And so that's kind of the initial aspect here too. But then New Horizon Technologies had originally worked with the Department of Homeland Security to develop a system that we are kind of taking and kind of furthering that development while working with them too. So a few kind of engineers and partnerships with them to really kind of take their technology and kind of push it further into the kind of adapt it to the mission for environmental management and site remediation here. So the system that we're looking at is originally so IGART is the official name. So that is the I would have to kind of look up the acronym there, but the Integrated Ground Agent for Radiological Tracking, I believe, is the official acronym. Hopefully I put this in later. This was developed in partnership with New Horizons as part of a small business initiative too. So this was originally targeted to perform radiological kind of site interdiction too. So as you're talking about planes entering and kind of making sure that we're tracking various contaminants or markers that would kind of identify radiological things being smuggled in or addressed there too. So part of this is then adapting that kind of initial kind of system here. So taking a kind of technology that had already been kind of worked on and really taking it and adapting it to the environmental management, site remediation system here too. So Los Alamos National Laboratory and the site office for the environmental management EMLA site office were identified as a candidate site for a couple reasons here too. So we do have a lot of areas at Los Alamos which has been operable, of course, for anyone who saw Oppenheimer since the 40s here, to really do a lot of kind of testing there too. And in the past, much of that testing occurred in kind of surface areas, and as the initial phases of the kind of atomic weapons process, that really involved a fair amount of low-level material being kind of exploded and dealing with these things there too. So this was kind of something that we had adapted there too, and we took this and really kind of adapted to an existing site that was part of a remediation campaign that was already being existed here too, which is the Petrillo and Fence Canyon aggregate area, which again I will kind of go into a little more detail about on this as we kind of go through the next set of slides. And then this was something that we were able to kind of demonstrate in the field last September. And so we will continue with this, and we'll talk about kind of the results of that demonstration along with kind of the updated plans here too. And so really, as I mentioned, is kind of an issue that's kind of inherent to adapting technologies here too. And so we kind of heard about this thing in really kind of the valley of death here. So when we talk about TRL levels, we really are trying, so technology readiness level is what we kind of mean there, but really taking things from that initial concept phase and going through even that, after we've kind of, proven a prototype in a laboratory environment, is how do we adapt that into kind of the real world application here too. And particularly for radiological kind of contamination work, that's something that's extremely difficult, because not only are we kind of dealing with the fact that most of these sites are not kind of amenable to access generally due to the hazard as well, but also just the kind of security hazards here too. So Los Alamos is still an active laboratory performing nuclear weapons development, nuclear work for other kind of applications here too. And so that involves all kind of security kind of concerns as we're dealing with kind of bringing things around here. So in terms of, as we're dealing with new unproven technologies, is how do we first find an area where we would have considered this as a operational kind of theater, so to speak, and then also how do we kind of take that technology and develop it into a kind of to a real world application here too. So something that a lot of the work kind of involves with proving things in this environment has to go through multiple hurdles, multiple approvals here too. So this is kind of what we're trying to target and what the Office of Technology Development is trying to work through here too. And so each of these kind of issues kind of involves multiple stakeholders too. So in terms of Los Alamos, the site managing their kind of security concerns, the environmental management field office, which is in charge of oversight of all the kind of remediation work being done. So those are two separate entities, along with kind of any contractors and subcontractors that are involved with kind of the work being completed there too, and really executing the work itself here too. So it's a complicated process, and really trying to kind of coordinate all of these stakeholders to really push forward and advance the technology into something useful for the end users here. So as I mentioned, the goal here is really for this MARSIM mapping process and data here too. And so what MARSIM is referring to, it's the Multi-Agency Radiation Survey and Site Investigation Manual. So as you may have surmised from its name, so this is something that has been developed as part of a kind of cross, contamination or cross, cutting group of different agencies to really define how do we assess, get a central framework to say, how do we define what contamination is? How do we deal with kind of surface contamination and mapping there too? So, and really for this is focusing solely on kind of surface contamination here too. Obviously, when we deal with a lot of these kind of legacy work sites, things have been moved around, and we'll kind of discuss that here in a sec as well too. So that kind of results in some subsurface contamination that really involves with soil sampling here too. But really what we're looking at now is just that kind of surface level contamination here. And so the main use for this, as I mentioned there too, is once you have kind of gone and identified a site that has some, legacy contamination, is how do we verify that once our work is done, that site is beneath the levels required for releasing the site, that it is, safe for humans to walk over, that it is safe for, a regular employee to work on as well here too. And so that's the kind of, end use here, but also at the various kind of states here, as you're doing things, you're constantly trying to measure and kind of assess your progress here too, rather than kind of, bite it off in one chew there too. But because this survey process is so kind of both onerous, and also, it exposes employees every time you're walking into an area with contamination, that's going to, provide dose exposure, that's going to provide contaminant exposure. And we're really trying to minimize the kind of that level of, exposure for employees and, workers here too. And then beyond this here, so while I said the primary use is really that status survey, MARSIM really defines a flexible procedure that kind of defines really a gridding that you're trying to do. So in terms of how many measurements you need to take, how many samples are defined, which is dependent on a kind of DQO process, so data quality optimization. So as you're dealing with areas that are kind of, dealing with higher release criteria in terms of what the end use of the site would be, that's kind of how you're defining the higher levels of, contamination, mapping to define your confidence level there too. So you can imagine something where if you were to be releasing it to, be a residential area, that would be a much higher level of fidelity that would be required versus releasing something that will just solely be a kind of empty field that will be restricted access there too. And so this procedure kind of covers each of those operations there too, to really provide, a flexibility thing rather than kind of tailoring each kind of individual use case to the what you're trying to define. So the site itself, so just to give you an idea of Los Alamos, so Los Alamos itself is, 100 or so square miles. It is a large site. We are very well spread out. As you might have imagined back in the day of when we were kind of doing the nuclear weapon development of, Oppenheimer. So that geographic remoteness really does kind of, provide the ability to kind of conduct testing in multiple areas. And so the current site is kind of defined as a relatively large area here. So you can kind of see the up at top there, that's the kind of Los Alamos town site and the kind of main office building area. And then this entire area down kind of, south of there represents kind of mostly where the firing site operations and a lot of the kind of legacy controls have been here too. And so as a result, much of the area is kind of in various states of operability versus inoperability in terms of legacy contamination versus active sites. So the site we are looking at right now is highlighted in this red circle. This is a legacy firing site that was used from 1946 to 1981, primarily, for uranium, depleted uranium, along with beryllium, other materials there too. So this was a surface site, and we'll have some more more information about that as well here too coming up here. So really what we're trying to do with this project, as I had mentioned here, is to take an existing platform, that was in that kind of, mid TRL level as far as, what it was attempting to do to really perform that radiological detection. We'll kind of go in and how it's doing that as well too with the technology, but also to take this and adapt it to a system rather than kind of having to go start from the ground up for these systems. Often with this work scope, we're looking for things that are really we can kind of plug and play here and drop in rather than being able to really take something from a concept and really drive it through. For us, the end result is the work scope for something, this is a couple years here too. So as we're kind of developing work plans, that's something where we really need to, take things and move forward here too. So we really have been working with so N3B is the contractor responsible for executing this remediation work, but working with them and the environmental management site office here to really define what the specifics they need in terms of the radiation detection capabilities, what kind of fidelities are required in terms of location, and that kind of work here too. So as I mentioned, it's a lot of partnerships here too. And there we go, the integrated ground-based agent for radiological tracking. So we can refer to the tape there to see how close I got it earlier. So a little more of the site background here. So what we're looking at is a zoomed in version of what I was showing you a couple slides ago. So TA15, so Los Alamos is defined into a series of technical areas. And so TA15 is where the kind of EF firing site is located. And so for this site, basically, this was something that was used starting in the mid-1940s. It's about 1,200 acres total, which is kind of represents the entire site boundary there too. And really, this is part of a larger cleanup plan, many of which is taking place at TA15 there, but really throughout the lab to execute a lot of kind of cleanups of hazardous waste that was kind of identified over the course of the years. Certainly a lot of work that was done in the past. Really, they were focused more on kind of advancement. And so as things were kind of left, they were not left in kind of, completely, cleaned up states there too. So really, as we kind of identify things according to kind of current, waste management kind of environmental standards, we're really going back constantly and kind of addressing the kind of legacy work and making sure that we're really maintaining the constant kind of, need to keep things at the current kind of standard here too. But the site we are is a subset of the kind of TA15 here too, and there will be some additional data. So as you can see, the Los Alamos town is located north of this. White Rock is just kind of another town, and we have kind of, national monuments around here too. So this represents that entire kind of Los Alamos laboratory site here. So like much of these kind of systems at Los Alamos, so we do have some existing surveys here too. So the latest survey for this site was conducted in 2010. So via a Fiddler walkover. So Fiddler is a radiation instrument. It's primarily used to perform gamma counts with low energy radiation there too. So this was conducted via a series of really employees pushing a cart over the site there to really survey the site relative to background radiation here too. So what we can see on the right here is the results of that survey. So as you can see, so there were additional surveys that were conducted in March as well too. So in the lower left-hand corner here, that's really a representative of the geometry we're looking at. In New Mexico, it is very much desert out here. So lots of sagebrush, lots of kind of, smaller bushes there too to navigate. But in terms of the contamination mapping here too, what we're seeing is the result of after they would conduct their kind of firing site experiments, they would take the kind of resultant soil and kind of bulldoze it into a couple mounds. And so as you can see, these higher radiation, sites there, those are representative of where they kind of had mounded the resulting kind of, outputs of their kind of explosive material there too. So what we are trying to do basically, rather than do this, via walkover, which is a multi-day process, which involves, large number of personnel, is take this robotic system and be able to kind of conduct these surveys, gather this data and these maps, in order to basically say, hey, this is what the state of the site is after kind of remediation here too, and before, to really get a sense of where, work needs to be targeted to in terms of being able to perform this work according to, environmental standards here too. So this is almost entirely the result of various isotopic uranium. I think basically every uranium isotope is represented here, and depleted uranium as well here too. So really at this point, the only radiological issue that we're looking for is that kind of, higher gamma count is what's being exposed here. But for kind of subsequent systems, they would be interested in really identifying down that isotopic discrimination as well too. Again, so in addition to the surface surveys, great part about a lot of our kind of legacy work here is that there has been a lot of work done to characterize the work here too. So each of these dots represents a kind of more thorough gridding with subsurface samples collected at each of the locations here too. So what we're seeing is a topographical map as well. So you can see the kind of mounds being highlighted. I mentioned there is the kind of larger setups there, which is where the higher contamination levels were noted here. So each of these dots represents an area where we have existing knowledge of the soil sample data as well too, which is largely in agreement with the kind of surface sampling as well too. Sorry. So again, just some more specs about the robotic platform. So this was the system pretty much as it was developed here. So most people who are familiar with some degree of mobile robots will recognize the ClearPath Husky platform here too. So with this one, this is a modified Husky, and we'll talk about what those modifications were done to really incorporate some additional sensors as far as robotic motion sensors and performance moves as far as LiDAR type work, but also to incorporate the radiation detection system here too. So for this one, has about a 5-kilometer range, and everything runs on a kind of raw setup via Docker containers there too. So the system itself moves at about 0.75 meters per second. So those are not unusual for any kind of Husky things there. But the incorporation of some custom battery platforms is really used to enhance the kind of range and system as well here to really improve the kind of capacity or two. Obviously, in terms of any time you're deploying a system onto a contaminated area, you're really trying to minimize the amount of time you're having to service that system and interact with it, because each time it kind of removes from a contaminated area until you kind of perform a full survey of that system, you are kind of dealing with a potential contamination issue that you're kind of developing. So as I mentioned here, so we do have some specialized microcontrollers that were developed to integrate the radiation sensors, which are 2x2 set of sodium iodide detectors in addition to a strontium iodide detector. I think we will have a little more data about that. And then in addition to a custom battery ecosystem. So it's hard to tell just going back here. Going back one slide here. So you can see the battery kind of, being loaded into these front thing. These are two setups there too. So the idea there is each of these battery systems, so they enable the system to run really at a kind of, full charge, performing its, measurements over the course of an entire day without really needing that kind of intermediate survey situation there too. The communication is just over a radio station, obviously, as I mentioned, in terms of dealing with the lab and various type things here. So that is a kind of bigger concern for us in terms of what we are allowed to kind of bring on and how we're allowed to communicate with systems here too. So really just a base setup to cover that kind of communication as we're dealing with systems. We don't have to deal with any kind of tethers or similar devices there too. So as I mentioned, in terms of the radiation detection system, so what we are looking at right now is a kind of CAD model of how it is designed or located within the platform itself, in addition to some modeling architecture on the right as well too. So on the left side there too, you can see the 2x2 array of sodium iodide for really anomaly detection, just kind of base levels of directionality there too. So for the current applications, since we are looking at the for surface contamination, so right now we have them pointed at the ground as well to really kind of better target that. Obviously, we do still deal with some mitigation through the body of the Husky itself too. in addition to those sodium iodide detectors, which are really for those gross gamma counts to really measure just general radiological contamination, there is a strontium iodide detector as well, which is located in the middle there. And that is for use to do that isotopic identification I was referring to earlier. So that's something that we are also kind of looking at incorporating some alternate detection systems, some CZT detectors that are now kind of really becoming available just in the last couple of years as far as being able to perform some of that mapping stuff. So those are systems from H3D as well. So this is kind of how it's performing the actual kind of radiation detector. And you can see from the image on the right here, the housing of the system as well too. So really that modification to the Husky platform and how we're kind of mounting to that system. So yeah, so in terms of what we're looking at, so for these detections, as I mentioned, we're primarily concerned about how we measure radiation relative to the background, and really kind of, X times the background here. And so what the sodium iodide systems are getting here too, and you can look at the HMI for the system. Really, this is a kind of sub window of what we're looking at. So with the full spectrum being displayed here too. And so what it's showing here is also really, that spectra here, but also the kind of counts per second from each of the different detectors as well, along with kind of defining alarm thresholds. So part of the goal here is really to provide this as a way for people that aren't necessarily, experts or SMEs in the field of radiation detection to provide actionable information here too. And so part of that is really defining, okay, as we're traveling over this contamination site, performing measurements, what do we consider an anomaly, something that needs to be investigated? What do we consider an alarm threshold? So really providing them with these kind of adjustable, are we in an anomalous area? Is this twice background? Is this 4 times background? That information for them to provide. Okay, do we need to further investigate this? Is this a location that will be something that can involve later here too? And the system itself also is generating this data constantly and really tagging it to GPS coordinates as well too. So as you're getting the kind of gamma detector counts, you're kind of really constantly generating a map of gamma detector counts tagged to GPS locations as well to really generate those maps kind of moving forward to provide that MARSIM and actionable data here too, as we're identifying where the contamination is and what levels the contamination are at. So again, this, like I mentioned, so all this is programmed via ROS2 here, so via an onboard computer here, but just a overall sense of where the information is coming from and what's going on in terms of how that's being adapted here too. So the wheel motors are involved, are obviously kind of being controlled there, in addition to a GPS and IMU device for kind of pose identification too, to make sure that we're really kind of moving on from that. And then, as I mentioned, so those custom boards to integrate the sensors here with the gamma detectors, along with a kind of LiDAR system to really provide a physical map of the system to really also, because part of the problem is here, as I mentioned, so we are not in a kind of flat area, completely cleared area. So really identifying, trees, brushes, rocks, obstacles that you would encounter in a standard desert environment. So being able to identify that in addition to kind of camera views is really important to the overall operability of the system. So, all right. And so these are from some of the earlier kind of demonstrations. As I mentioned, the system was originally developed first for interdiction purposes, so really detecting as our radiological agents being kind of identified in here too. So the original pose identification simulations were done kind of via airplanes as a DHS type application here too. But then this is kind of as we're doing the SLAM algorithms via sensors and kind of with the IMU information for the real-time pose to come out of that to generate the obstacle maps to really let it kind of move around the environment without necessarily like only relying on camera data. So what we're looking at here. And then beyond that, as far as, just some additional data as far as what we're doing in terms of being able to adapt things. So this is kind of also as we're tracking the kind of control of the robot via joystick. So when we're teleoperating, as I mentioned, so this is, via joystick operation. So being able to adapt that kind of, input from the joystick, so that haptic, and as we're kind of driving things around to be able to do that kind of pose identification and monitor where it's at, in addition to just not solely relying on the GPS data. Right now, we have only really been operating in external environments, so outdoor areas. The end use would eventually require operating in, potentially indoor areas and kind of GPS-denied environments to really be able to say, hey, we're doing that mapping without, solely being reliant upon a GPS kind of system here. And so a big problem, so as I mentioned, part of the concern here is being able to provide a system that operates, that does not require, the robotic SME out there to operate here too. So a lot of work kind of just had been developed a little bit in terms of being able to identify the state of the system, what information needs to be provided to the user for, actionable operation here too. So this is what is displayed on a base station with the system here too. So we have, a stand-up system with the location of the robot itself mapped onto a kind of, so this is a, GPS. I can't remember if we pulled this from Google Maps or whichever here too, where the robot is located, in addition to the kind of active count data. So the 1.08 is referring to the measurement of radiological contamination relative to background there too. So as you kind of scale that up, you're able to define what the actionable issue is there too, with a as you're getting to rather twice background, 4 times background, 10 times background here, to really give the operator a sense of where things are at here too. And so that's why we have the kind of color scheme there, in addition to the detector information being shown in the kind of counts per second area too. So each of the 2x2 detector sodium iodide sensors is shown with the kind of current counts per second, along with the kind of strontium iodide count per second as well too. In addition to that kind of full information that's shown as a rolling average in that bottom left kind of graph there too. So as you're seeing with this has kind of been driven over a slightly higher contamination area than that was kind of moved into as it's moving along. You see that kind of rolling average, which is adjustable, count dropping into a lower area there too. Beyond that too, just some sensor, metrics there too. It's the temperature, making sure things are functioning right there, in addition to the kind of battery and radio strength to make sure that the system is involved there too. And at the same time, we also do have a active kind of GPS location being shown, in addition to pose information, which is resettable, obviously, of course, between your X, Y, and your rotation. Obviously, we don't have to worry about Z with a ground platform here too. And so then in the upper right, that's an image we just pulled from for security reasons. But this would be kind of as you're actively driving the system, it has a kind of camera on the front that's letting you kind of guide to where systems are, in addition to the LiDAR data being shown to monitor and prevent collisions. Oops. So yeah, so just a couple of sentences. So this is originally from a demonstration at Savannah River, so in your guys' backyard there too. So this was part of their initial demonstration to really be able to validate the performance in a kind of what we would consider a more laboratory environment here too. So there were they were able to create a fully encapsulated, fully characterized environment by placing sources underneath these cones as necessary, and verifying that the system is able to kind of detect contamination sealed sources that are located under kind of one of the cones there, basically too. So this is kind of the operation and kind of showing the system as well too. And then as the is located in an area where there is no contamination, that's really where we're defining that background information. And then in kind of more this similarly, so this was also still at Savannah River, not at Los Alamos, but what this looks like in a kind of more field environment, but still kind of an artificial environment with contamination really being controlled there, rather than being located in an actual environmental site like we are kind of operating at Los Alamos here. And so this data is basically from those, again, contaminated sites here. So on the right here are not contaminated, laboratory sites, more or less. So you can see what the system looks like in terms of the data being gathered relative to background information for the image or sources being placed underneath cones. You can see this cone here represents where the radiation source was, and you can see as it would drive by that you'd be generating those higher count values, in addition to kind of environment that was located in a tractor trailer there too. And so in terms of what we were able to do in September here, so looking at the site relative to the previous background we had, so we were able to kind of perform a couple different surveys there too relative to the initial system here. So the rough location of these surveys, and I'll show some of the data here in a sec, would be located in these two kind of areas there too. So this really corresponds to areas that were easily accessible. It's you can tell here that there is a road located down. You can see this kind of L shape there too, that provides us with a great staging area, but also in this upper left area, there is some additional, base course that is built up that is kind of not considered contamination area, a contamination area that we're able to use as well. So what that looks like. So what we're looking at here is actually a couple. So the top image, these are both maps, more or less. So what we're looking at is latitude and longitude here. So really the course of a robot as the robot would travel through. And it's a little difficult to see. The areas we were operating in did not have, some of the higher contamination there. But really looking at those kind of, field maps and seeing those kind of heat maps as we're kind of identifying, driving the robot through some of the areas here too. So you can see some higher, background radiation contamination noted in certain areas as the kind of robot was moving around there too, and being able to kind of map that onto what the existing maps were, generated via the existing, the approved kind of, survey methodology. And what we're looking at the bottom left is really just kind of the initial data we had gathered, kind of moving the robot from, like I said, this uncontaminated kind of road area. And really the second we would move it onto the contaminator, you can see the kind of increased, background levels there as it kind of moves, from this uncontaminated area in the upper right, then driving it. So it was a pretty instant kind of just reaction there too. And so for that, really just kind of demonstrating the kind of, so this is not a super high level of, contamination, but just the, instant exposure, hazard that you're exposing people to really just by walking into the area there too. And that is, you can see the longitude difference, latitude differences there are, extremely minor, and that's kind of just the difference in where we're dealing with and what the kind of site situations are looking like here. And then a better sense, so as I had mentioned there, in terms of being able to overlay that with some of the information here. So some of the pathing that we had done here too. So this was very much us, really trying to get a better sense of what, as we're performing some of the surveys, this would not be, you would have a more defined area in terms of, much more back and forth in terms of being able to make sure you're looking for. This was really some of our initial kind of validation work where we're trying to drive amongst the areas where we expected to find contamination. So really what this kind of, end result of that mapping would look like here too. So this is a much more kind of smeared data rather than what we're looking at via the walkover surveys too. But when you're talking from a Markson perspective, then you're really quantizing that down to individual points to generate something that looks a little more akin to like this here too. So as you can see in that kind of lower right area of the map we're looking at now, you do see that kind of, a direct, increased area of the contamination there too that we were able to kind of identify with the robot itself as it was kind of moving through the area. So just some additional photos, as I mentioned on. So this is what you kind of mentioned with the base course setup too. You can get a good sense of what the robot itself looks like in the current state. Some members of the interagency working group, Los Alamos employees here too, and what the camera looks like, in addition to some of the sensors on the front, and a better sense of really what the kind of, specific obstacles and terrain is looking like in the EF firing site there too. So this is mostly represents areas that has been, previously, like I said, not where the mounds are of the kind of higher contamination, but really just the kind of areas where experiments and explosive experiments existed in close proximity to where the robot was taking some of the measurements along that path. So right now, so the current plan or the current system during that initial deployment, that really was deployed in a fully teleoperated environment. Obviously, with the LiDAR system, the onboard computers there, the onboard GPS location, there's nothing really preventing that from, incorporating those additional autonomy. So via waypoint navigation, via defining, as I mentioned, so with the Marson map generation, you're defining that gridding system based off, pre-known, parameters there too. So really, as you kind of define a, I need this map of this area to this fidelity, that's something you know beforehand. And so being able to include those parameters to output a kind of path planning algorithm into the system is really what we're working on at this point here too, to incorporate that autonomy so it is less operators on the day of are kind of driving through, making sure they're hitting their sense, versus operators that are more operating in a kind of supervisory manner to say, we're deploying this and ensuring that it's completing its, task, it's completing its path without really any additional need for information here too. So that's ongoing and something we're really working with in terms of the end users and how they want to define in terms of what parameters need to be included and then involved in how things are kind of moving out there here too. Oh, sorry, yeah, just hopping on to David's question here, saying here, yes, that is, so right now, so that's something that varies per site. So the question is about gamma spectroscopy versus gamma counting. So for this application, sorry to jump around here too, really the concern is about gamma counts here too. So right now we have a good sense of what the isotopes and what their kind of distribution are at the site here. And there's just due to legacy information there too. We have a good sense of what kind of experiments were conducted there. And for them, they're mostly concerned about, for this site at least, in terms of just gross kind of gamma counts and the radiological contamination that way. In terms of other sites, and this kind of combines with the kind of alternate materials here, those kind of isotopic identifications and doing that spectroscopic work is something that's relevant for them too, and being able to say, okay, now we have a better sense of what specific isotopes we're looking at in what quantities there too. It's just something that for this site specifically, we're trying to really target the system here too. So that was the kind of concern there too. Right now, we are not using collimators on the system. As I mentioned, with the fiddler detectors being the kind of baseline we're adjusting for too, it really is something that we're operating from a relatively low fidelity system that we're kind of targeting the system here too. And so for this, they really have, not a huge need for very specific, very targeted information, but really being able to kind of identify things to within, a 5-foot type location here too. So that makes the problem statement relatively easy from a detection perspective. At the same time, that does kind of limit the need to do a lot of that, really targeted work to improve the detector fidelity. One of the things we're looking at in addition to kind of the alternate XRF materials is really trying to do some of that targeting work for applications that do need some things. Obviously, with the Husky platform, there's additional levels of attenuation in terms of the robotic platform being in there as well too. So that's going to limit your radiation detection capabilities as well too. And so that kind of ties into the robotic mobility options. But really the XRF and heavy metals, in addition to that isotopic discrimination there too, is ties to the other kind of missions of the EM kind of site remediation kind of problem there too, since radiological contamination tends to be one of only many contaminants that are present at these sites that needs to be addressed here. As I mentioned, kind of with the site description there, really a big concern at the EF site as well is beryllium. So beryllium, cadmium, arsenic, some of those devices there too, and a system that can detect radiological contamination is great, but being able to kind of adapt that, because really the detection needs, are very similar in terms of locating and identifying what devices are there too. So really being able to modularize the system to be able to kind of adapt to multiple different, non-radiological hazards is something that has been a real, key point for the environmental site here as well too. And then in addition to that, so we have been doing some work, as I mentioned too, just showing from here, really taking this data and adapting it to the existing ones. But this is a site that's also going through ongoing work, so ongoing surveys here too. So really deploying that with their, actively approved, surveys to really generate that comparison data to be able to say, hey, these are, a system that we have, proven that we have kind of generating that, to use that to really advance that into those kind of higher TRL level, to say this is not only proven in a kind of active operating environment, but also that we are kind of generating valid data that matches with kind of existing systems, just at a kind of more a more kind of operationally easy kind of way to do this. So something that exposes workers to less of a hazard, something that's able to be executed with, fewer support personnel, that kind of work there too, to really let workers execute the work in larger areas without kind of having to, deal with, all of the kind of fielding and staging operations required to execute a walkover survey there. And so I think that's all I've got. David, thanks for your questions. I'm happy to open up to any other questions here, Walter, Leo as well.
Well, Bryan, thank you so much for your presentation. It's excellent. So this time we're gonna go ahead and open up the floor for anyone who has a question for Bryan.
A quick question. Can you hear me?
Yes.
Yeah.
Related to like radon, I have found doing background surveys that certain times of the day, radon outgasses, and it can drastically increase the amount of radiation you see. Have you seen that?
So for this one, we haven't. So that's something that really the background survey questions that really this ties into David's question as well too. Something that we've really been kind of, I wouldn't say fighting, but working with the kind of existing process owners to say where we are kind of defining background radiation, how we're defining that too, to limit those issues there too. And how, so because, yeah, that is something, is particularly at Los Alamos as well. So we are at, 7,000 feet here. So really that, and, addition to really the entire site to some degree has, some level of background, levels there too. So making sure that we're matching to existing process to control for that radon, because as you say, that's a system or an issue that is kind of inherent to radiation measurement that, rather than necessarily one to the system as well here too. So really being able to better kind of target that to make sure that we're controlling in the same way so that we're generating kind of similar data as to approved kind of methods there.
All right, Bryan, looks like we have a queue of questions here. I think, Anthony, can you go ahead first?
Hi, how are you? Nice presentation. Thank you so much. And you answer a lot of questions. We also work with radiation mapping, and you answer us a lot of questions. So anyway, so on this slide 24, you show that one of the biggest challenges in radiation mapping is to do the gamma reconstruction, using some sort of Gaussian process, particle filtering. You guys thought about what would be the best method for large areas? I know some people use nearest point, others people use most of famous Gaussian process, but you have any thought about how to convert those point clouds in a dense area that guides your robot where that the uncertainties are high?
Yeah, no, that's a great question, a great point, and something that, yeah, it's been another thing we're kind of ongoing dealing with here too. One thing, obviously, as you would probably have guessed for these things, is the quantity of data being generated here is pretty large. And so just the process of kind of extracting the data off the kind of system, the raw data. I mean, this is a day-long process to extract, just a day's worth of information or an afternoon's worth of information here too. And so quantizing that down from, this kind of smeared point into, something like the, more akin to, these, specific individual things here. That's something that we're trying to kind of work with. And this kind of ties into Daniel's question as well in the chat here, as far as regulators accepting the data. Right now, they are not. I'll be upfront there too. But as far as what, how we kind of define that in terms of, whether this is, as you're saying, one of the processes too, versus, saying, hey, we are snapshotting data, every, 3 feet, or how we're kind of smearing that into the process here too. And so that's something that really for us has been defined by the ultimate regulatory authority. and how they would like the kind of data presented here too. So our current approach so far has been to generate as much data as possible, and then being able to kind of do that post-processing into a level that would be necessary. And so really we haven't kind of reached out a final resolution on that point, but it's a great issue and it's a great question, a great problem to highlight there too, because yeah, that is a, how we're defining, not only where the radiation is being, developed or, gathered, but how we are kind of, displaying it, right? How we're kind of quantifying that level of, issue beyond, displaying, like 500 gigabyte, maps over a process here too, because as you say, when like over a 1,200 acre site, like that's just not feasible. And so quantifying that down into what level of, what level of kind of issues need to be involved there too, or what level of data needs to be displayed to provide a useful map, that's also tied to the Marsan process too. And so really for them, it's it depends is kind of our process, or at least what the information we've gotten, and we're really trying to push back and get some of that information narrowed down in terms of what they need and what kind of smoothing or kind of quantizing it would be involved there too, as you say.
Bryan, thank you for answering Daniel's question as well. Daniel, if you have a follow-up, let us know. Let me go back to the hand raise. Phil Moore.
Hey, it's Leo. Sorry, a little explanation. We're having the end of semester class presentation, so we were taking a little break to listen to Bryan's presentation, and Philip happens to be logged in. But anyways, Bryan, when you were doing the seal point, the seal source measurements, obviously under the counts, were you moving or you stopped, do the counts, and then go to the next one, or how was that done?
Yeah, so that was New Horizons work as part of their DHS project. So that was something that they came to us that we were able to kind of review on that. My understanding is that it was a, I guess I would call it a single blind type experiment with a, source kind of located. I'd have to look back at what this specific source is, like a cesium-137, I believe, source kind of being hidden under one of the cones. And part of the question is, as we're driving the kind of robot past this, it was kind of collecting that data here too. So if I can go back to what that, so yeah, so this site here, so each of these points, again, a little bit quantized there too, represents a, snapshot basically of as we're kind of driving the system back. And you can see it's, snapshotted by time more or less. So you can see as the system, had identified a higher contamination point, it was kind of moving at a slightly kind of, slower speed to really make sure it's gathering data there as well at a higher kind of fidelity. And then as it kind of, moves into this area where it was not identifying kind of systems, then driving at a faster speed there too. And that really ties into something that has been highlighted as a capability. And I had mentioned as far as the some of the work with the anomaly detection there too is one thing. Speaking with the environmental management site managers here is really being able to say, okay, really that fidelity of measurement, we don't care as far as, when we're just getting those low levels, background levels. It is okay if we, speed things. But as we kind of develop some, higher measurements, that's where we need to really say, can this thing do that, have that level of autonomy to pause and say, okay, this is something where we do want to get those additional kind of, count data here to really better target that source and kind of adjust that speed down, or really just, kind of pause and gather additional data so we can better locate that and target it. And so for this experiment, I believe this was, really involved just a kind of moving system, but, at an adjustable speed more or less here too.
That's great. Hey, Bryan, there's another question from David.
Mm-hmm.
Yeah, just one of the things I was going to say is that you're talking about anomaly detection. With gamma spec, it's not uncommon to get 30 to 50 times lower than the background level. In other words, I can go by a cesium source, detect it with radiation that's 30 to 50 times less than background, but because I'm looking specifically at the gamma energy line and there's very little background there, whether it's airborne or ground-based, I can detect, again, 30 to 50 times less than the background number. You can't do that when you're counting.
Mm-hmm. Yeah, and part of that too is really targeting for us, and what we've spoken with them is that modularity. So for them, this application in particular, this was something that we have a, very specific known source here that they have, really kind of, because we have a lot of sense of, even if things, weren't necessarily like extremely well documented in terms of, the process going on, the overall contamination, profile, so to speak, there too, is pretty well known. So for this, they have already kind of identified what energy needed to be detected there too. For sites that are kind of more unknown, so to speak, in terms of, what contaminants we would expect here too, it would require a much more specific, detection platform or detection, solution there, really, right? And so part of that is really why we're saying, we're making sure that, for these easier, so to speak, systems where we're just detecting, DU, isotopic uranium, we're targeting a, appropriate detection platform that isn't, the Cadillac, so to speak. But then when those detection platform or those detection, contaminant profiles do require that sort of, very specific, much better sense of, where we're really trying to identify, isotopes and contaminants there too, then we would really be able to take the same, remote system, same remote interface, and being able to apply it to a much more kind of, appropriate detection platform that really would be, more useful, more, tailored to the thing like you were mentioning there too. Because yeah, in that application, like you're saying, a gross scanner detection system would not be, very appropriate, as we're saying.
Guys, great questions. Anybody else? Any other questions? David, is that you again, David?
Yeah, just
Okay.
I have one final one, and just that at some sites like Fernald and other places where when we did our analysis of contaminated sites with uranium and such, we went to a neighboring site and we found that the background varied almost by a factor of 2, just the natural background. And then the time of the day, like I said, the radon coming out of the ground also was almost another factor of 2. So it now all of a sudden becomes time dependent, and the compaction of the soil depends on how much radon comes out. So there's variability as much as a factor of 2 in some of these sites that I've seen just based upon gross gamma counting. So again, the challenge with gamma spec is if you don't go slow, you can't gain enough spectrum information in 1,000, however many, channels you use. You can't get good statistics.
Mm-hmm. No, absolutely. That's a great point there too. And yeah, so that's kind of why we, in this period, as we're saying, this is a something where we've been relying upon the kind of existing processes and define for, how we're being told what to use as background kind of measurements here too, and really mapping to the kind of existing, processes, approved procedures there, rather than, trying to tackle that problem on our own, which is, as you say, it's, very challenging and something that's, kind of inherent to the process than necessarily with deploying a robot out there too. But being able to really, say we are kind of addressing things in the, same manner is kind of how we're trying to really tackle really Daniel's question as far as being able to, present this to regulators as a, valid solution to say, yes, we're dealing with these problems, but we're dealing with them in the same way as the kind of other systems that you have previously accepted.
All right, so we're going to leave the last question for Anthony. Anthony, go ahead.
Hello. So it's fascinating, this idea of moving measurements. I always have in my mind that I have to stop and wait for the quality of the measurement go up. But actually, it's very interesting that you guys move around and we can speed up and slow down, so we can cover very large areas. So this is a technology that developed by Newer Horizon.
Yes, so obviously, a Husky platform is a ClearPath robotic platform, but in terms of the overall interface and being able to integrate that with the system and incorporate that functionality, it is useful, as I said, to the radiation detection problem there too, and being able to adapt the measurements as David had mentioned here too. A gross gam measurement by itself is not particularly useful, but being able to at least adapt that to some version of, we are presenting this into a useful interface for a environmental application, but also being able to provide them with that functionality rather than saying, hey, here's a Husky I can go buy and I can drive it around. But how do I generate data that exists in a format that is, potentially useful to generate the Martian mapping data, but then also to be able to kind of provide operators and the end users, which are the kind of cleanup contractors, the remediation contractors, say we can deploy this without having 3 or 4 grad students being involved to field the system, kind of deploy things out there too. So really taking it from that kind of lower level, this is something that exists mainly as a prototype, to really integrate it into a here's a deliverable sense of saying here's something you can use, and without necessarily an oversight from all of 4 different experts in robotics and detection there.
All right. With that, let me give me about 2 more minutes. We have a couple of announcements here to make. First of all, let me thank Bryan for his excellent presentation. Also, let me thank the Department of Energy and Environmental Management for sponsoring this Tech Talks. Our next Tech Talk, please save the date for July 16, 2024. If you can go ahead and scan the QR code, you can send us some feedback on this Tech Talk. But I want to leave you with this last slide here. Let's see. There you go. And I'm going to have Dr. Lagos go ahead and mention the robotics AI workshop we're having next week. If you have any, Dr. Lagos, can you hear us?
Yeah, so thank you, Walter. Just we have the next week robotic AI workshop. I know our colleagues from Los Alamos are coming, other DOE national labs and sites and contractors. So again, this is more for the community to enrich the community, and the lessons learned and all that we're going to discuss next week. We'll make that part of our knowledge base, perhaps using KMIT platform, but anyone online is invited to participate. So we'll be happy to see you in Miami next week. Turn it over to you, Walter.
All right, thank you so much, Dr. Lagos. Well, once again, thank you for Bryan for the presentation. Thank you for the Department of Energy and Environmental Management for the support of this effort. Thank you, everyone, for attending. It's been great engagement at the end there. And I guess this will officially end this meeting.
Thank you,
very
Walter.
much.
Thank you, Bryan.
Thank you, everyone.